Okay, so today we're going to be talking about continuity. And so the first thing I'm going to do is I'm going to define what it means for a function to be continuous. And then I'll kind of break it down into steps as to why we need kind of a certain number of conditions to be satisfied in order for something to be continuous. And of course, I'll give you kind of like a visual explanation of it, which hopefully will basically clarify why these steps to follow are important. Okay, and so let's define what it means for a function to be continuous at some specified value. So we can say a function f is continuous at a number a if the limit as x approaches a of f of x equals to f of a. Okay, so in fact, if you look at this one statement is saying three things, okay? And so if this is saying three things, by definition, to show something is continuous, we need to show that the three things that this is saying are satisfied. So what are the three things? So here's what this means. So just to break it down, and of course what I'm writing down here, these are pretty much the steps we're going to follow. So this means three things. One, f of a exists. So in other words, if I plug in a into this function, I better get an output, which basically that's what this is saying. The second statement is the limit as x approaches to a of f of x exists. So in other words, this two-sided limit here must exist. And the final step is, see, just because f of a exists and the limit as x approaches to a of f of x exists, it doesn't necessarily mean that my function is continuous at x equals a. The final step is step 1 and step 2 must equal, which is basically where this comes in. So not only does this need to exist and the two-sided limit needs to exist, they also need to equal each other. Okay, and that's where kind of this comes in. So when you look at this, it doesn't look like much, but in fact, it's saying three things. Okay, so keep in mind that just because steps 1 and 2 exist, it doesn't necessarily guarantee that my function is continuous. Finally, we need to make sure step 1 and 2 are equal to each other. So basically, this is telling us 1 has to equal to 2. So if any one of these three fails, then of course our function is not continuous at that value. Okay, so however, I want you to go through all three steps. So if let's say f of a doesn't exist, we already know that my function is not continuous, but I want you to go through all three steps and show all three steps and then specify why something's not continuous and so on. So visually speaking, here's what's happening. If I want to show a function is continuous at a, what do I need to do? Well, first of all, we need to show that f of a exists. So if I plug in a, I get some output, f of a. Okay, and then what I need is the two-sided limit to exist. Now, see, if I were to draw out, let me use just a different color. See, what if I have step 2 exists, but it looks like this? See, if I draw a function that looks like this, what do you notice here? The limit as x approaches a of f of x also exists. However, we could see that this isn't continuous. How come? Because we have kind of like an opening here, or think of it this way. If something is continuous, that means if you walk along that path, you won't fall off. But if I'm walking, there's an open point here and I'll fall off. So clearly it's not continuous here. Now what went wrong? Steps 1 and 2 are satisfied here. However, this open point needs to be, in order for this to be continuous, this open point actually needed to be closed up by that point. So that's why this would not be continuous. However, what I would really want is something like this, which notice now if I kind of get rid of this down here, this is continuous at A. How come? The two-sided limit exists, the value is defined at A, but the two-sided limit and the value of this function defined at A all agree. So that's it's kind of like we're closing the gap. Okay, so clearly we could also see what goes wrong if any one of these fails. See, if f of A doesn't exist to begin with, that means I have probably an open point at A, or I have a vertical asymptote, which means right away it's not continuous. Now, if the two-sided limit doesn't exist, then one example would be if I have something like this at A. So clearly we could see that there's a break here. So it's important to show all three steps. And if any one of the three steps fails, then it's clearly not continuous. Okay, so before we do a few examples and kind of define a couple more things, I want to just talk about the different types of discontinuities. So let's look at example 1. So for example 1, we want to state where each function is discontinuous. So I'm basically telling you these functions aren't continuous, and we want to find out where they're discontinuous. And each type of discontinuity has a specific name, and that's kind of what's important here. So if I give you f of x equals x squared minus x minus 2 all over x minus 2, my question to you is, where is this guy discontinuous? And I think you guys are pretty good at looking at this and being able to tell me, hey, look, this won't be continuous when my denominator is 0. Okay, but then the question is, what type of a discontinuity is this? So we could already say that this is discontinuous at x equals to 2. Now, what type of a discontinuity is this? Which that's also important, because if you look at this, we know that it's either this is going to be an open point at x equals 2 or a vertical asymptote. The difference is if I could cancel out the x minus 2, that'll be an open point. If I can't cancel it out, it's going to be a vertical asymptote. And sure enough, if you notice, if I factor the numerator, it's x minus 2 times x plus 1 all over x minus 2. And so the x minus 2's will cancel out, and I'm left with x plus 1. So the graph of this guy is actually a line with an open point at x equals 2. So the type of discontinuity this is, its name is, so the type is actually removable, which I hope it makes sense to us of why it's called removable. It's because it's like as if you're removing a point. So the graph of this, if I were to draw it out, it will be at x equals 2, y is 3. We put an open point, and then that's the graph I have, which notice how this has a removable discontinuity at x equals 2. Other than that, it's continuous everywhere else. Okay? So let's move on to the second part. If I have f of x equals to 1 over x squared, if x doesn't equal to 0, and 1 if x equals to 0. And see, here's the nice thing, what I like about this question. See, if you look at this question, the domain of this guy is all real numbers. However, it doesn't necessarily mean that it's continuous everywhere, because see, if we were to graph this, what do I notice? As I get close to 0, 1 over x squared does what? It goes up to infinity. So if I were to graph this, let's just focus at 1 over x squared for now. So let's graph the top part of this piecewise function. We know that 1 over x squared looks like this. And at x equals 0, we're told that y is 1. Now you could see there's something going on here. This is clearly not continuous there, because first of all, of our three steps we're checking which one fails. the condition fails where the limit as x approaches 0 of f of x, because if you're approaching 0, you're not necessarily equal to 0, so you use this guy, and it goes up to infinity. So you could see that our second step, where you check the two-sided limit, that's non-existent, which gets this to fail, which we could see that there's an opening here. We can't close this off and make it continuous. So what type of a discontinuity is this? Well, just by looking at it, what happens to my graph as I get close to 0? This goes up to infinity, which means it's called an infinite discontinuity. So we would say this is discontinuous at x equals to 0, and its type is infinite. Okay, so let's move on to the last type of discontinuity, which goes to our beloved step function, which we've been seeing so much over and over. So if we were to graph this, what is it that we notice? And I'm sure you already know what the graph of this guy looks like. So if I were to graph this, we notice that it's like our step function, right? And when you look at this and think about it, how many discontinuities does this have? Well, it has discontinuities almost, or it has infinitely different places where this is discontinuous, because where do we notice? Where do our discontinuities occur? It's basically where we have this jump from here to here, right? There's a break here, a break here, a break here, a break here. So all of my discontinuities happen where? At the integers. Other than that, everywhere else it's continuous. So the only place that I get discontinuities here for this are at the integers. So we could say this is discontinuous at each integer. And the type of this is called a jump discontinuity. Obviously, we could see why it's called jump, because from here all of a sudden just jumps up, right? It leaves kind of like this gap here, and then it jumps up here. So these are all jump discontinuities. Okay, so in fact, there are three types of discontinuities we're going to see in this class. One is removable, which is just identified by an open point. The other one is infinite, where when you get close to that value of interest, your graph goes up to infinity or down to negative infinity. And there's a jump discontinuity, where it just jumps from one y value to the next, which those are the three types we'll deal with. Now, we also have one-sided continuity, which you know, unless we're told to do so, we'll check for a one-sided continuity. But in this class, when you're checking for a continuity, you check from both sides. But there are functions that we may just be interested in. Hey, is this continuous if I approach it from one side? So the definition is very similar. There's just one slight difference. So what we're saying is a function f is continuous from the right of a number a if the limit as x approaches a from the right side of f of x equals to f of a. Okay, and so notice how, what are we doing here? You're just saying you're approaching a from the right side of f. So this is still saying three things, except when you're checking your limit, if it exists, we only care about it from the right side. So basically, the limit as x approaches a from the right side of f of x has to exist, f of a has to exist, and those two must be equal, basically. So that's what we're doing here. And we could also define it from the left side. We could say f is continuous from the left side of a if the limit as x approaches a from the left side of f of x equals to f of a. Okay, so basically this is talking about being continuous from the left and from the right. So let me show you an example where we could talk about continuity from one side only. So back to our step function, here's what we could say. So for example 2, we'll say the function f of x equals the greatest integer of x is continuous from the right but not left at each integer. Okay, so we know that the discontinuities occur at each integer, but if we're specific, here's what we could say. Look, limit as x approaches a from the right side, and we're assuming a is an integer, and there was a homework problem assigned. What is it that we notice? If you approach the greatest integer, if you approach a from the right side of that function, if you remember, you get a. We did this for homework. If you remember, instead of a, we called it n. And it doesn't matter. If you approach it from the right side of any integer of the greatest integer function, you get a. And what do we notice? If you plug in a, for example, if I plug in 2 here, the greatest integer less than or equal to 2 is 2 itself, right? So this is a. So what do I notice here? The right side limit exists, which is a. At a, it's a. And what do we notice? Since limit as x approaches a from the right side of f of x equals to a, or f of a, this is continuous from the right side of a. But from the left side, here's the problem we run into. As I approach a from the left side of f of x, what did you remember? What did you notice from the homework when you did this? The limit as x approaches a from the left side of f of x, that becomes a minus 1. And f of a equals to a. And so what do I notice? This is 1 less than whatever that is. So we could say not continuous from left side of a, since limit as x approaches a from the left side of f of x does not equal to f of a. And that's where we get this discontinuity. Okay, so that's what we need to keep an eye out for. And so notice how I'm trying to verify all 3 steps. Maybe I should have done a better job. I should have said step 1, like this is the first thing we do, second thing, and then the third thing is a statement where we make. Okay, same thing here. Step 1, step 2, third statement we make. Okay, so let's move on. And what's going to be nice in a minute, we're going to get a theorem that's kind of going to give away to us where functions are continuous. But before we do that, let's kind of define what a function, when a function is continuous, or how we consider it to be continuous. So a function f is continuous on an interval if it is continuous at every number in the interval. So what makes this a little different than what we've been doing is now we're focusing on actually infinitely many values, right? If you notice, so far we focused on, is it continuous at a? And a was a specific value. Now what we're saying, a function is continuous on an interval, which when you talk about an interval, like even if I give you the interval from 0 to 1, there's infinitely many numbers between 0 and 1 that we can find. So we need to show that it's continuous at every number in that interval. And the problem with that becomes, well, since there's infinitely many numbers, I can't check every single value because I'll never get to the end. So we need to generalize this. So in example 3, we're going to do that, and we're going to just generalize what's going on here. So here's what we're going to say. We're going to show that the function f of x equals to 1 minus the square root of 1 minus x squared is continuous on the interval -1 to 1. And see, I'm going to break this up, or I'm going to only do one part of this problem, but you guys could probably do the other two parts. What do I need to show? To show that this is continuous at every number from -1 to 1, there's three things I need to show. I need to show that this guy's continuous on the open interval from -1 to 1. Okay, how come? Because, see, at -1, if I use the original definition of continuity, I have to take a two-sided limit, but I can't go to the left of -1. So if I can't go to the left of -1, I just need to show that this is continuous as I approach -1 from the right side. And then I have to show that this is, so at the end, at 1, I also need to show that this is continuous as I approach 1 from the left side. Because when I get to 1, the two-sided limit isn't going to work, because the second I go to the right of 1, I'm out of bounds. But the good news is the steps are going to be the same. So here's what we're going to do. So for case 1, we're going to say let a be a number between what? -1 and 1. And see, what's the problem we know we're going to have? I know that as long as the number inside of the square root is positive, I can get an output. But if it's negative inside, then what happens is we run into a problem. And so the good news is -1 to 1 is actually what the domain of the square root is. See, if I plug in, let's say, 2 here, I get 1 minus 4, which gives me a -3 inside of the square root, which is a problem. But the good news is I'm from -1 to 1, so I don't have to worry about that. As long as I'm between -1 and 1, 1 minus x squared is going to be a positive number. So basically, I'm generalizing it. And see, the reason why I'm generalizing it is because there's infinitely many numbers between -1 and 1. So this is a way that I'm allowed to capture all values starting from -1 and going to 1. So here's what we could say. Then the limit as x approaches a of f of x is the same thing as the limit as x approaches a of 1 minus square root of 1 minus x squared. And in this case, the good news is I could use direct substitution, because as long as this doesn't have any cuts or breaks or discontinuities or anywhere that it's not defined, I could just plug in a and use direct substitution, which let's actually go through with this. So limit as x approaches a of 1 minus the limit as x approaches a of square root of 1 minus x squared. Notice how I'm allowed to do this because I'm just using the properties of my limits. And what do we know? The limit as x approaches a of a constant is always just a constant. And then here I can say minus square root of, I could take the limit inside the root. That's another one of my properties. And now what I notice is 1 minus x squared is a polynomial function. So I could just plug that in. And as long as what's inside of the square root isn't negative, I could go from here to here. And the reason why I was able to take the limit inside is because I know that this isn't negative. So I could do that, which is a valid move. Which, what does that give us? That gives us 1 minus square root of 1 minus a squared. Which, technically speaking, that's the same thing as what? Me just plugging in a for x here, which is the same thing as f of a. So what did I just show? I showed that the limit as x approaches a of f of x is the same thing as f of a. Okay, now I couldn't do this in the three-step mode because, like I said, we have infinitely many values, so I had to generalize it this way. Okay, so we showed that this is continuous from -1 to 1, not including -1 and 1. Now, the second case would be, and I'll write the cases here, and then you could go ahead and do this, but case 2 would be show it's continuous show continuity as A approaches -1 from the right side. Okay, so we want to show that this is continuous as A approaches -1 from the right side, which technically speaking, it's the same steps as case 1. The only thing that will change is when you approach, you see how this is a two-sided limit? It's just going to be a one-sided limit, which means you're going to be approaching 1 from the right side. Okay, so instead of A, you're going to have 1, and I'm sorry, not from the right side, it's going to be -1, and you're going to be approaching, yeah, and it'll be from the right side. So basically, these steps will be the same. A will be replaced with -1, and there'll be a plus because you're approaching from the right side. And then case 3 would be A would be replaced with 1, and you'd be approaching 1 from the left side. So once you show those, then you've shown that it's continuous on the closed interval. So, and then case 3 would be show it's continuous as A approaches 1 from the left side. So these are things that you should just try out on your own, but they're pretty much the same thing. Okay, now the next couple of theorems that we talk about, these are going to be very helpful for us, especially when we talk about the second part of this section, and it's going to be, we're going to use these theorems. Now, these theorems don't have names, so we don't need to refer them to their name, but as long as we make the appropriate statements, then we have nothing to worry about. So you could say, if this function is this type of a function, we know it's continuous on its domain. I know that you're referencing these theorems. So here's what the first theorem that we're going to put to use quite a bit. So you could say if f and g are continuous at A and C is a constant, then the following functions are also continuous at A. Okay, so what we're doing here is we're just stating some conditions here. So what's nice about this theorem is the following. If f and g are continuous at A, okay, now don't worry about the constant. You'll see where this constant comes in from in a minute. But if f and g are continuous at A, then what we're saying is f plus g is also continuous at A. Okay, so it's kind of nice. So in the future, when we work on certain problems, I might give you two functions and say, look, is there some continuous at A? Well, you would say, look, since f is continuous at A, g is continuous at A, then their sum will be continuous at A. And by you making that statement, you're referencing this theorem. Now, since it doesn't have a name, you don't have to reference it by name. But by you just making that statement, I'll know you're referencing this theorem. So you don't have to worry about saying, hey, there's a theorem that says this. I know that's basically where you're referencing it from. Okay? It's the ones that have names that I really am picky about, that you need to make sure that you give credit where credit is due. Okay? And then, of course, f minus g is also continuous at A. And then, of course, a constant times the function will be continuous. And this is where the constant comes from. So if f is continuous at A, then any constant times that function will still be continuous at A. And then f times g will also be continuous at A. And then finally, the last one that we have is if f divided by g is continuous at A, as long as if g of A doesn't equal to 0. Of course, we don't want our denominator to 0 out. So we know that these will also be true. Okay? So basically, what we're noticing is the last example we did, we're coming up with more efficient ways of saying, hey, look, these are continuous. They're proven. So what we did in the last example, unless we're asked specifically to do it that way, we can just reference these theorems and just say, hey, look, since f is continuous, g is continuous, their sum has to be continuous. So I could have come back here and said, look, what do I know? 1 is always continuous from -1 to 1. Square root of 1 minus x squared is always continuous from -1 to 1, which means their difference will be continuous from -1 to 1. Now, for the square roots, we're going to touch up on that in a minute, because you could say, well, how do I know that this guy is also continuous from -1 to 1? Well, the next theorem is actually going to do that for us. So this next theorem, what it does is it gives us a bunch of other functions. So think of these as kind of like tools. We have a bunch of tools where we get an easy way or a quick way of saying something is continuous somewhere, okay? So here's what we could say. The first theorem says, or this next theorem says, any polynomial function is continuous on the real number system, which is from -infinity to infinity. So what's nice about this theorem is you could say anytime you have a polynomial function, you could say it's continuous on all reals. Okay, and once again, why is this theorem so nice? Because we get these for free. You don't have to prove this unless I specifically tell you to prove it. Okay, but if you ever have a polynomial function and the question is, where is this continuous? Well, you'd say, since it's a polynomial function, it's continuous everywhere. And what are you doing? You're kind of putting this theorem to use. So what's nice about these theorems is we can make these statements. We could just use these theorems freely, okay? And then we could also say any rational function is continuous on its domain. So once again, what's nice about this, if you ever have a rational function and I ask you, look, where is this continuous? You could say, since it's a rational function, it's continuous on its domain, which is all these places, and you specify its domain. Now, let's be careful though. If I say, is this rational function continuous at a specified value, now that I'm going to specifics, then you have to show me the 3 steps that we talked about, the first thing we talked about earlier on. Okay, so before we go on to our last theorem, I just want to make a comment here. This we already know, which is some trig function stuff. Limit as theta goes to 0 of sine of theta, that's going to be 0. And the limit as theta goes to 0 of cosine of theta, that's going to be 1. Okay, so to wrap up this section, we have our final theorem, which what this next theorem does is it just makes things even better. It says, look, here's a list of a bunch of functions that are continuous on their domain. So if you notice the theorem before this, we were specific to polynomial functions and rational functions. And then the one before that is just talking the sum, difference, product, quotient of a bunch of functions. So here's what we could say. This last theorem says these functions are continuous at every number in their domain. So here's a list of all the functions that are continuous on their domain. And the first couple we've already seen. So the first one we talked about were what? Polynomial functions. So we could say polynomial functions. And then the second one was, of course, rational functions. And then here's a bunch of other ones that we haven't talked about, which is root functions. And so like in the example 3 where we worked with root functions, this was one of them. All right, we could have said since it's a root function, it's continuous on its domain, and its domain is from here to here. So that's kind of what's going on here. And then we have trig functions. Trig functions are continuous on their domain. So whatever their domain may be, we know they're always continuous. Of course, if trig functions are continuous on their domain, inverse trig functions will be continuous on their domains. And then we have exponential functions. And the last one, which of course, if exponentials, they're inverses, which are logarithmic functions. So let me kind of give you the difference. So when do we take the 3 steps to show that a function is continuous? It's when you're asked to check, hey, look, is this function continuous at x equals 2, for example? So then you take the 3 steps. You check out, well, is it defined that, is f of 2 defined? And then do I, as the limit as x approaches 2 from both sides of 2 of f of x, is that defined? And then you check, well, does f of 2 equal to the limit as x approaches 2 of f of x? That's when you take the 3 steps, which those are at specified values. When do we use these guys? Well, when we're talking about intervals, right? Because look, when you talk about their domains, these are intervals. So if I were to say, for example, where is, I give you a root function and ask you, where is this guy continuous? Then you'd say, well, to tell you where this is continuous, we know that root functions are continuous on their domain. And see, the second you say that, you're referencing this theorem. So even though it has no name, you're referencing it. And then you'd say this root function has domain such and such, and on that domain, this guy's continuous. And so that's good enough for us. Unless you're asked to physically prove it, which will be rare. I think we're going to use these theorems more often than just physically prove it, like in example 3. Then you could just use these freely. So these are kind of like, they're going to be to our advantage, because especially when we get into the second part of this section and we use a bunch of, we're going to be proving things, we want to put the theorem to use over and over and over. Okay, so that takes care of the first part of section 5. Next time around, we'll cover the second half of section 5. Okay.